Good morning, class. Today we're going to continue with our exponential and logarithmic unit. We're going to introduce ourselves to some logarithmic functions today. All right, so we're going to start off by trying to find the inverse of y equals 2 to the x. So we talked about how to find inverses a couple of units ago. All right, and basically how we get that started is we just go ahead and switch the positions of x and y. All right, and then we have to solve for y. Okay, well, that doesn't really help us out a whole lot, right? So another way that we talked about finding inverses, right, is if we have a set of points, all right, we can switch the x's and the y's. So if this is 2 to the x, which we actually did yesterday, so we can use these same points, right? And here we will get 1/8, 1/4, 1/2, 1, 2, 4, 8. All right, well, if that's the case, then f inverse of x we literally just switch all of these. So 1/8, -3, 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2, and 8, 3. All right, so if we go ahead and graph all of that, all right, so we started with 1/8, -3, and then we had 1/4, -2, and we had 1/2, -1, and we had 1, 0. All right, then we had 2, 1, 4, 2, and 8, 3. So if we connect this with a nice smooth curve, right, this is our inverse of y equals 2 to the x, which is y equals log base 2 of x. All right, so if we talk about the kind of attributes of this, we can consider this somewhat of a parent function, although the base, of course, can change. Just like with exponential functions, even with the base changing, right, it's going to be the same general shape and it's going to have these same general attributes. All right, so the domain here, all right, is going to be from 0 to infinity, not including 0. Okay, we'll hug this line here, but we'll never actually get to it. Our range, we go down forever, we go up forever. So this is all real numbers or -infinity to infinity. All right, an intercept, we don't have a y-intercept, but we do have an x-intercept of 1, 0. All right, where is this graph increasing? It's increasing everywhere. All right, do we have an asymptote? We do. We have this vertical asymptote that as we kind of approach 0 here, all right, we will approach the asymptote of x equals 0. And that's all of our basic attributes of a logarithmic graph. All right, so definition of logarithm, all right, I definitely do not like the letters that they use here. All right, so I'm going to kind of write my own logarithm, definition of logarithm here. All right, I do log base b, because that's your base, so it should be b, of a. This is actually called the argument of the function. That's why I call it a. All right, that is equal to c, and I just call it c simply for alphabetic purposes there, a, b, c. All right, if and only if, which this is a mathematical symbol for if and only if, all right, b to the c power is equal to a. All right, so this piece here is called logarithmic form. Obviously, it has a log in it. This piece right here is called exponential form, obviously, because it has an exponent. All right, so this will allow us to jump back and forth between the two forms anytime that we want. Okay. Again, only these letters will make it much, much easier for us. All right, so it says write the logarithmic equation in exponential form. So again, if we have our definition of logarithm, log base b of a is equal to c if and only if b to the c equals a. All right, then basically, right, my b is 4, so this becomes 4. My c is 3, all right, and my a is 64. And numerically, it's fairly easy to check this, right? Is 4 cubed equal to 64? Yes, of course it is. All right, so we can go ahead and do the same thing here. We can say 7 to the negative second power is equal to 1 over 49. Is that true? Yes, it is. Remember, yesterday we mentioned negative exponents. Right? If you have a negative exponent, you can flip that base between the numerator and denominator, wherever it's at, change it, and you can make the exponent positive. So 7 to the negative second power is the same thing as 1 over 7 squared, which obviously is 1 over 49. All right, and then here we can do the same thing. Do be careful. They've kind of flipped, the log is on the right side this time, but that's okay. All right, so this is 32 to the 2/5 power is equal to 4. All right, that one's not quite as obvious to see, although this is a good opportunity to have a quick little refresher over fractional exponents. All right, remember with fractional exponents, the numerator kind of remains an exponent, so this would be squared. The denominator is actually the root, right? So just kind of off to the side here, this isn't really part of that problem, just as part of the explanation. All right, 32 to the 2/5 power is equal to the 5th root of 32 squared, right? So the denominator is a root, the numerator is still a power, and honestly, you can put the power under the root or outside of it, it doesn't matter. But in this case, I think it's easier to put it outside because we can find the 5th root of 32, right? So what can you multiply by itself 5 times to get 32? That's actually 2. All right, so then we still have our squared. Okay, well, that equals 4. So yes, right, you can kind of see that this is a true statement. All right, write the exponential equation in logarithmic form. So now we're going the other way. All right, whoops. All right, so now we're still going to have our definition of logarithm. Log base b of a is equal to c if and only if b to the c equals a. All right, and this double arrow, this biconditional, means that you can go either way, right? I can start here and I can go here, or I can start here and I can go here. All right, so in this case, I'm starting with my exponential form and I'm going to logarithmic. All right, so here we will say log base 5, right, of 125 is equal to 3. We can do the same thing here. Log base 6 of 1 over 36 is equal to -2. And here, again, of course, be careful. They switched it around a little bit on us here, but we can still say log base g of 4 is equal to a. All right, so again, this is very, very important. That is one thing that you will definitely need to know for this upcoming test. Okay, use the definition of logarithmic functions to evaluate the functions at the indicated value of x. All right, so it gives us an x here, so I can say, all right, y is equal to log base 2 of 16. All right, well, this isn't obvious. You don't just necessarily look at this and know what it is. So sometimes it helps to put it in the other form. So this is in logarithmic form. Let's go ahead and put it in exponential form. If I put it in exponential form, it tells me that 2 to the y power is equal to 16. Okay, well, 2 to the first power is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth power is 16. So I know that y has to equal 4. Right, down here we get a little bit tougher. Right, you may want to pause this video and try it on your own here. See if you can get it. It's a little bit more difficult. All right, so we do the same thing here. We're going to have y is equal to log base 16 of 1/4. So if we switch that to exponential form again, all right, we're going to get 16 to the y power is equal to 1/4. All right, well, this is tricky, right? Because obviously 16 to the first power is 16. 16 squared is a giant number, all right? So we can't be doing that, all right? So we actually have to go, and we know that this is in the denominator, so we're actually going to have a negative exponent here. And how can I get from 16 to 4 in terms of exponents? All right, as we talked about with fractional exponents, exponents and roots kind of go hand to hand together. All right, so we actually want to take the square root of 16. Okay, well, the square root of 16 is 4, and that's to the 1/2 power, is the same thing as the square root. All right, that's very important to note. All right, so x to the 1/2 power is equal to the square root of x. X to the 1/3 power is equal to the cubed root of x, and so on and so forth. All right. But if we just do 16 to the 1/2 power, that's just 4. I want it to be 1/4. So in order to get that in the denominator, I simply just have to make it negative. So y equals negative 1/2. All right, the common logarithm. All right, the common logarithm is log base 10 of some argument a. All right, and when you have log base 10, you don't even have to write the 10. All right, you can just actually say log base a. Log of a. And that's understood when there is no base. It's understood that it's base 10. Okay. So let's go ahead and use a calculator to do this. All right. First one we don't really need a calculator for, right? Log base 10 of 100, all right, equals something. You can make it an x, you can make it a question mark. So if you write this in exponential form, 10 to what power equals 100? Well, that obviously equals 2, right? 10 squared. These other ones, however, we will need a calculator for. All right, so we can say, okay, and remember, log base 10 is just log. So if you just hit this button, that's automatically just log. So I can do log of 1/5. There we go. All right, I can do log of 3.25. There we go. All right, log of -4. All right, now this one's going to be a little bit more interesting. All right, we get an error, and it tells us, all right, that it's not going to be a real number. All right, so that's a domain error. All right, if you go all the way back to our graph, all right, remember the domain of a standard log function is 0 to infinity, not including 0. So you can't plug negative numbers into here. So that's actually why we got that error. right, here are some properties of logarithms. All right, so log base A, and I don't like this again, but it's fine. I would usually make all these B. All right, so log base B of 1 equals what? Well, B to what power equals 1? Well, B to the 0th power equals 1, right? Anything to the 0th power is 1, right? B to what power equals B? Well, B to the first power equals B. Right, here we would ask B to what power equals B to the x? Well, B to the x power equals B to the x. Right, and then this one we're going to use a lot when we solve logarithmic equations. All right, so it's kind of important to note, even though it's very common sense. Right, if log base b of x equals log base b of y, then what must be true? All right, well, if my bases are the same, the only way that these two things can be equal is if x is equal to y. All right, so here, solve and simplify. All right, this is a typo actually, so we'll just go ahead and skip that one, but this one's easy enough, right? 4 to what power equals 4? Okay, well, x is equal to 1. All right, 5 to what power equals 5 to the x? Well, 5 to the x power equals 5 to the x. All right, and 7 to the log base 7 power equals 14. All right, well, let's go ahead and kind of put this back in logarithmic form, right? This is actually exponential form, right? So if we have our definition of logarithm, log base b of a is equal to c, if and only if b to the c equals a. All right, so this is actually in this form, even though there's a log in it, it's part of the exponent, right? So if I rewrite this, this is log base 7, and we want to know what this equals, right? So log base 7 of question mark equals this exponent, right? So log base 7 of 14. Well, this gives me that if log base b of x equals log base b of y, then what must be true? Well, x must equal y. All right, the natural logarithm. Yesterday we talked about that kind of a new number that we call e. We found by finding the limit as x approached infinity of 1 plus 1 over x all to the x power. Right? We said that was e, which just comes up to be like 2.7182 ... All right, so the natural logarithm is actually log base e of some argument a. All right, but we never actually really write log base e. Log base e is the same thing as ln. So whenever you see ln, that's the natural log. All that is log base e. All right, so we can do these again using our calculator. All right, so we have an ln button right here under the log button. So ln of 2. Awesome. All right, ln of 25 works out just fine. Now, what do we expect to happen here? All right, well, just because my base is e, that doesn't change the general shape and my attributes of the kind of parent function of a logarithmic curve. So again, we aren't allowed to plug in negative numbers here, so we should expect to get an error, and we do. All right, properties of natural logs work identically, really, to the properties of just the common log. All right, so remember, this is just log base e. So e to what power equals 1? Well, e to the 0th power equals 1. All right, again, this is log base e. So e to what power equals e? E to the first power equals e. Again, this is log base e. So e to what power equals e to the x? Well, e to the x power equals e to the x. And again, if ln of x is equal to ln of y, then x must equal y. All right, so use the properties of natural logarithms to rewrite each expression. All right, so here we have ln of 1 over e. So this is basically, remember, all right, this is saying e to what power equals 1 over e? All right, well, that equals -1, right? E to the negative first power, that flips its position from the numerator to the denominator. All right, so here we have e to the ln of 5. All right, well, the e and the ln essentially are going to cancel out. All right, but again, if you wanted to put this in logarithmic form, all right, you would say log base e of question mark equals ln of 5. Well, remember, log base e is ln, right? So ln of question mark equals ln of 5. That's if ln of x equals ln of y, then x must equal y. So question mark has to equal 5. Essentially, these just cancel out. You can think of them that way. All right, 4 times the ln of 1. All right, remember, the ln of 1 we said was 0. All right, well, 4 times 0 is just 0. All right, the ln of e, we said that was just 1. All right, well, 2 times 1 is 2. All right, ln of e over 6, we just said the ln of e was 1. All right, so this is just 1 over 6. All right, and of course, your homework will be on Delta Math, and that is all we have for today. Have a good day.